Today we are going to study two-dimensional wave equation. Okay, and as a special case, we shall study the vibration of a rectangular membrane. Okay, so first let me write down the wave equation when we consider that dimensions more than one. So wave equation. We already saw that in one dimensions, the wave equation is given by dou to u by dou t square is equal to c square dou to u by dou x square. Okay, this is the one-dimensional wave equation. When we have more than one dimensions, maybe 2 dimensions, 3 dimensions, then there is a small change in the right-hand side. The left-hand side remains unchanged. So in 2 and 3 dimensions, we have the wave equation is written in this form. This is equal to c square Laplacian of u. Okay, this is Laplacian of u. This is 2 and 3 dimensional wave equation. Okay, 2 and 3 dimensional wave equation. Here, Laplacian of u in Cartesian coordinates in one dimension, it reduces to dou to u by dou x square. So this is the most general case. This equation is true in any coordinate system, be it Cartesian, be it cylindrical, be it spherical. This equation is always true. Okay. So we are going to solve this wave equation in 2 dimensions. Okay. And as a special case, we are going to study the vibration of a rectangular membrane. We are going to study the vibration of a rectangular membrane. Okay. Say, for example, when you beat the table, the drum within. So when you play drumming on a table, how does the table oscillate and how does it produce the sound? Table the table oscillate and how the table produces that sound. We are going to study that. So for simplicity, let us consider a thin vibrating membrane. Okay, a rectangular vibrating membrane. And let us also assume that the vibrations, that is the displacement, are also small compared to the size of the vibration. And this membrane is a homogeneous membrane. That is, the mass per unit area in the membrane is uniform throughout the membrane, and then the membrane is stretched with some tension T. Okay. So the equation in Cartesian coordinates, the wave equation in Cartesian coordinates is a 2-dimensional wave equation in Cartesian coordinates. Is dou to u by dou t square. This is equal to c square dou to u by dou x square plus dou to u by dou y square. This is the wave equation in 2 dimensions in Cartesian coordinates, where u is the displacement, where u is a function of x, y, and time is the displacement of a point with coordinates x and y of the membrane. From rest. So displacement from rest, okay? And rest is given by u equal to 0. And at time t, here u is the displacement. This u is the displacement of a point with coordinates xy of the membrane. And this displacement is measured from the mean position, and the mean position is the rest position, r rest position given by u equal to 0. And this u xyt is the displacement at any time t. Okay. And the boundary conditions are, or in short, the boundary condition is u is equal to 0 on the boundary, of the membrane. Okay, the boundary condition is that there is no displacement on the boundary of the membrane. That is, the membrane is fixed at the boundary. And I repeat here, this c square, this is nothing but the tension divided by mass per unit area. Okay, and the boundary condition is u equal to 0. That is, the membrane is fixed along the boundary in the xy plane for all times. And what are the initial conditions? The initial conditions are the initial conditions at t equal to 0 are: number 1, u x y 0, this is equal to some function f x y. Okay, so this is the initial displacement. Okay, so this is the initial displacement. That is the initial shape of the membrane at time t equal to 0. Okay, then the second initial condition is the initial velocity of the membrane. So that is given by del u by del t. Okay, dou u by dou t calculated at x, y, and t equal to 0. And this is given by g of xy. Okay, so let us write, let us give this equation as number 1, equation number 1, the boundary condition as equation number 2, and the initial conditions, these are given by 3a, equation number 3a, and equation number 3b. Okay, so this is the initial displacement, that is the initial shape of the membrane, and this is the initial velocity of the membrane. Okay, and we see that these conditions are quite similar to that of a string, vibrating string. Okay, so let me write it on a new sheet of paper. So for a rectangular membrane, let us consider a rectangular membrane. This is the x-axis, this is the y-axis, and let us consider a rectangular membrane which is placed in the xy plane. The length of the membrane is given by a. So the membrane stretches from 0 to a along the x-axis, and the membrane stretches from 0 to b along the y-axis. And this region inside the membrane, we can call it R. Okay, so we have considered a rectangular membrane R, and tomorrow we shall discuss a circular membrane like the drum head of a tabla. Okay, then the boundary condition, there is equation number 2. This boundary condition, it can be written in an easier way. Okay, so the boundary condition says that the displacement along this line, this line, this line, and this line, the 4 edges of the rectangle, the displacement along the four sides of a rectangle is 0. Okay, so we're going to solve this in 3 steps. In step 1, what are we going to do? We are going to separate variables. First, we are going to set u as a u xyz, u xyt as some function f times g, where f depends on x and y and g depends upon t. Okay, so first let us try to obtain ordinary differential equations from the given wave equation by using separation of variables method. Okay, so step number 1. Step number one, we apply 2 successive separations of variables to obtain ordinary differential equations from the given partial differential equation. So in the first separation, we set u x y t this as f of x y multiplied by g of t. So f is a function of position, that is, it depends on x and y, and g is a function of time. Okay, so substitution into equation 1, substitution into equation number 1. And what is the equation number 1? Equation number 1 is the wave equation. So we substitute u equal to f times g in this equation number 1. And we get, so substitution into equation number 1. So this is equation number 1. So if we substitute u equal to f times z in equation number 1, so what does it become? Second order partial derivative of u with respect to time. It becomes f times second order derivative of z with respect to time. This is equal to c square. Here g can be treated as a constant because this differentiation is with respect to x and y. So we should have c square. Then this is d2f by dx square times g plus d2f by dy square times g. Okay. Now, to separate the variables, what do we do next? We divide both sides by c square fg. So to separate the variables, we divide both sides by c square fg. We divide both sides by c square fg. And what do we get? If I divide this by c square fg, I get 1 by c square g. Okay. d2g by dt square. And this is equal to 1 by f dou 2f by dou x square plus dou 2f by dou y square. Okay. Now we see that the left hand side depends only upon t and the right hand side depends only upon x and y. Therefore, both sides must be equal to a constant. So since the left side depends only on t, whereas the right side depends only upon x and y. So that means it is independent of t. So the right side is independent of t. It's independent of t. Therefore, both sides must be equal to a constant. That is, both sides must equal a constant. Equal a constant. And as done earlier, we can show that for 0 and positive values of the constant, we find that the solution is identically 0. So the only possibility is that the separation constant should be a negative quantity. So by a simple investigation, we see that only negative values of that constant will lead to solutions that satisfy the boundary conditions given by equation number 2 without being identically 0. Without being identically 0. And this is similar to what we have done in the earlier cases. Okay. So denoting the negative constant by by minus nu square. This is the Greek alphabet nu. By minus nu square, we have, what do we get? We get this is equal to minus nu square. So we have 1 by c squared g d2g by dt square. This is equal to 1 by f dou 2f by dou x square plus dou 2f by dou y square. This should be equal to the constant minus nu square. Okay. And this gives two equations. So let me write it on a new sheet of paper. So this gives two equations. First for the time dependent function. First for the, let us call it time function. First for the time function gt. We have the ordinary differential equation. That is, now I multiply both sides by c squared g. So it becomes d2g by dt square equal to minus nu square c squared g. And then I bring it towards the left. So I should have d2g by dt square plus, I should have c square nu square g. And if I write c nu as lambda, then we have lambda square g. This would be equal to 0, where lambda equal to c times nu. Okay, so let us call this equation number 4. So this equation, it gives us two ordinary differential equation. The first is the ordinary differential equation for the time function gt, which is given by equation 4, and for the amplitude function, we call it the amplitude function f. amplitude function. Amplitude function f x y. This will initially give a PDE, partial differential equation. This will initially give a partial differential equation because it involves partial derivatives with respect to x and partial derivatives with respect to y. So for the amplitude function, there is f of x and y. We shall get a partial differential equation, and this equation is called the two-dimensional Helmholtz equation, Helmholtz Helmholtz equation, which is this. So if I multiply the both sides by f, then this becomes dou 2f by dou x square plus dou 2f by dou y square equal to minus nu square f, and I bring it towards the left-hand side. So we should get dou 2f by dou x square plus dou 2f by dou y square plus nu square times f. This is equal to 0. And this equation, we write it as equation number 5. And this equation is called the Helmholtz equation after the German physicist Hermann von Helmholtz, and this Helmholtz is known for his basic work in thermodynamics, fluid flow, and acoustics. Okay, so this is what okay. So this is the Helmholtz equation. Now we are going to separate the variables again. So we shall have one x dependent function and y dependent function. So separation of the Helmholtz equation is achieved if we set f of xy as the product of two functions h, which depends only upon x, and q, which depends only upon y. Okay, so we can separate the Helmholtz equation into two ordinary differential equations by setting f of xy as a product of two functions h of x and q of x, where h is a function of only x and q is a function of only y. So by substitution of this, into equation 5, into the Helmholtz equation, into equation 5, we obtain, what do we obtain? So this is partial derivative with respect to x. Now it reduces to total derivative with respect to total derivative of h with respect to x. So it reduces to the total derivative of h with respect to x to twice. Then q is a function of y, so it can be taken as a constant, and I take the remaining terms towards the right with a negative sign. So this becomes minus now dou 2f by dou y square. So this is partial differentiation with respect to y. So we can treat h as a constant. So h d2 q by dy square plus u square. Okay, nu square, and what is f? F is equal to hq. So this can be written as nu square hq. Okay, so to separate the variables, next what do? We divide both sides by hq. So to separate the variables, we divide both sides by HQ. And we get, what do we get? If I divide both sides by HQ, this becomes 1 by H d2h by dx square, and this becomes 1 by q d2q by dy square plus mu square q. Okay. Now we see that the left hand side is a function of only x, while the right hand side is a function of only y. So both sides must be equal to a constant. So by the usual argument, both sides must equal a constant. Okay. And we can also show that this constant must be negative, because only negative values will lead to solutions that satisfy the boundary condition without being identically zero. So this constant must be negative. This constant must be negative, and let us call it, say, minus k square. Okay, minus k square. Because so this constant must be negative because only negative values will lead to solutions that satisfy the boundary condition given by equation number 2 without being identically zero. Okay, without being identically zero. Thus, we should get, so let me write it on a new sheet of paper. So both sides must be equal to a constant. That is what we obtain here. So I should get, so both sides of this should be equal to a constant. That means 1 by h d2h by dx square. This is equal to 1 by q d2q by dy square plus mu square q. This should be equal to a constant, and we have named the constant as minus k square. Okay. So, so this yields two ordinary differential equations, two ODEs for h and q, namely, so first I take this and this. Now I multiply both sides by h. So this will become d2h by dx square equal to minus k square h. And I bring it towards the left. So I should have d2h by dx square plus k square h equal to 0. We call this equation number 6. And from this, we should get d2q by dy square plus, so if I multiply both sides by q, so it becomes d2q by dy square plus mu square q equal to minus k square q. And now if I bring it towards the left, I should get two terms containing q, mu square q plus k square q. And I take q common, so and mu square plus k square, I can write it as another, here, let me tell you one mistake which we made. Here we have a minus sign here, and we forgot to put the minus sign here. So let me insert the minus sign. This is negative. So that means This is negative. Okay, so that means now I multiply both sides by minus q. So I should get d2q by dy square plus nu square q minus k square q. And I take q common, and this nu square minus k square I write as p square. So p square q equal to 0. This is equation number 7, where p square is given by nu square minus k square. Okay, so we started with the two-dimensional wave equation, and we have obtained 3 ordinary differential equations. And out of these 3, we have 1 ordinary differential equation for the time function g, and we have 2 ordinary differential equations for the space-dependent parts h and q. Then we come to step number 2. Step 2. What do? We put the boundary conditions and find solutions that satisfy the boundary condition. So step number 2 is solutions satisfying the boundary conditions. The boundary condition. Okay. So the general solutions of equations 6 and 7, these are simple solutions. So general solutions of equations 6 and 7 are given by, h of x, this is equal to a cos, here we have k, so we should have a cos k times x plus b sine k times x. And for q, we should have two more arbitrary constants, and let us call those arbitrary constants as c and d. So c cos, here we have p, so we should have cos py, sorry, this should be q of y. So py plus, let us call the fourth arbitrary constant as d sine py. So this is the solution of equation number 6. This is the solution of equation number 7. With constants a, b, c, d. Okay. And we already know that from u was written as f and g, and the boundary condition equation number 2, it follows that this f, which was written as h times q, must be 0 on the boundary of the rectangle. On the boundary, that is on the edges x equal to 0, x equal to a, y equal to 0, y equal to b. So let me show you the picture again. There is the picture. The boundary of the rectangular membrane is fixed. So at x equal to 0, this is the edge we have. This is the edge, and at this edge, the displacement is 0. That is u is equal to 0. And x equal to a, this is the edge. This is the edge given by x equal to a. So the membrane is also fixed at this edge, along this edge. So the displacement here is also 0. Similarly, the displacement is also 0 along the edge y equal to 0, and along the edge y equal to b. So along the 4 edges of the rectangle, the membrane is fixed, so the displacement is 0 along these 4 edges. Okay, so this gives the conditions. There is h when x equal to 0, h is 0. Okay, Then when x equal to a, h is again 0. When y is equal to 0, q is 0. And when y is equal to b, q is 0. Okay. So let me write it on a new sheet of paper. Now, if you look at the first condition, when you put x equal to 0, h is 0. So when you put x equal to 0, this becomes cos 0. Cos 0 is 1. So 0 is equal to a plus, what is sine 0? Sine 0 is 0. Then this term will not appear. So from this first condition, we should get 0 equal to a. That means a is equal to 0. So this we done yesterday also. So this we have done earlier. We did similar reduction in earlier cases. Okay. So hence h0 equal to a equal to 0. So the first condition it gives us, this first condition it gives us that a equal to 0. And then h at a equal to b sine ka, and this is equal to 0. Okay.